Thank you for joining this tutorial session online. Today, myself and Massimo will talk for about 1 hour each slide. So I'm going to introduce randomization-based neural networks, and then I will skip oblique random forest. I don't think we will have time. Then I will pass on to Prof. Massimo Panella. He will talk about applications to time series. So my coordinates are here and my GitHub page is here. So you can get some resources from these pages. There's an iconic conference in Indonesia going to be online. I think the submission deadline passed, but this IEEE SSCI 2021 is still on. So if you have some works in any of these computational intelligence area, you can submit your work. Today, I am going to mainly talk about random vector functional link network. This one was introduced in 92-93 period. It has a closed form solution. So if you are going to train a single hidden layer network, you can obtain the trained network in one step. But if you want to go for multi-layer networks, then you have to apply this closed form solution multiple times. Rvfl has good scalability property, except when both the number of training samples and the number of features, both of them are very large. Very large means I am talking about more than 10,000. So you have more than 10,000 samples and each sample has more than 10,000 features like. In such situation, Rvfl will find it difficult. And I have some details about random forest. Maybe I will skip those details for today. And the slides are available from me for the random forest also. So the only topic I will cover today is randomization based neural networks and mainly the Rvfl. So the neural networks have a very long history. Starting from maybe 1950 and so on. And then in 1980s, it became very popular with the introduction of backpropagation training algorithm. So the multi-layer network can approximate any function to any desired degree of accuracy. And this universal approximation property was proven in the late 1980s. So you have the theoretical proofs here for the universal approximation property of the neural networks. So in the late 80s and early 90s, researchers identified some weakness of the backpropagation training algorithm. So the error surface usually have multiple local solutions, slow convergence, parameter selection problem, and so on. As an alternative method, researchers suggested randomization-based approaches. Parameters in hidden layers can be randomly generated and kept fixed. So there is no training. Only the parameters in the output layer can be computed, and for that you can just make use of least square solutions, and you have a closed form solution with a global optimum. So all these networks are collectively known as the randomization-based neural networks. So in the next slide, I am going to list a number of independent publications on randomization-based neural networks. The meaning of independent publications is there is no citation of each other in all of these papers. And recently, we compiled all these works together in a short paper titled On the Origins of Randomization-Based Neural Networks. And this one was published in 2021. We also have a survey from 2016 on randomization-based neural networks. So going to this list of methods published independently on the randomization-based neural networks. In 1992, this work was published by Schmidt and Duin. And in my opinion, this is one of the earliest that we were able to locate for the single hidden layer feed-forward neural networks with random weights between the input features and the hidden layer. So all these are for single hidden layer neural networks. And the next one is Rvfl. So this one was published in 1994, and we are mainly focusing on Rvfl because it performs better compared to all others. Then of course there are a lot more independent proposals of the same concepts. In 94 we have this one, and then in 95 and 95 another one. It was published in ICONIP conference. Then there is another version in 1999. And then the very popular extreme learning machines published in 2004. And the most recent independent publication of randomized neural networks is 2013. So this is called no-prop algorithm. And this one is for multi-layer networks. So among all these randomized neural networks proposals, Rvfl and ELM have several follow-up applications. So we will look at the structure of the Rvfl. It is a single layer feed-forward network with direct links. So these are the direct links, and this is really unique to Rvfl. Then you have input layer, one hidden layer, and the output layer. And these connection weights between the input layer and the hidden layer are randomly generated and kept fixed. So this is what we call the randomization. So these connection weights are randomized and kept fixed. No training for these weights. So during the training stage, we need to compute only all these weights. We call them collectively beta. So the parameters W indicated by blue are randomly generated and kept fixed. The direct links, what the direct links doing here is to concatenate original input features with the outputs coming from the hidden neurons. So the outputs of the hidden neurons will be concatenated with the input features. That is what the direct links are doing. So the learning, as usual, aims at ideally obtaining the true class label yi. Yi is the true class labels of the training data at the output. So the output values are obtained by a simple dot product operation. Dot product between connection weights beta and the data values. So this data value actually includes outputs from the hidden neuron concatenated with input features. So what they represent, I have already mentioned. O is the output, D is the data. So X is denoting the input data. For example, N number of samples and M number of features. The W, as I mentioned, the weights between the input features and the hidden layer, and these are randomized. Bias is also randomized, and we have activation functions at the hidden layers. So hidden layer neurons can have any of these activation functions: sigmoidal, radial basis function, or exponential, ReLU, and so on. And in recent times, we found out that ReLU and CLU are better for classification. And if you are doing regression or time series forecasting, we found sigmoidal is usually better. And for classification, ReLU, CeLU are usually better. And the capital H actually represents the outputs from the hidden layer neurons for all the training samples. Capital X represents the full training data. So capital H represents outputs from the hidden layer neurons for all of the training data. That is what's shown here. And the capital D is the data matrix. It is the concatenation of outputs from the hidden layer neurons H and the input data. So they are concatenated. So these are the outputs from the hidden layer neurons, and these are the original input data coming through the direct links, and they are concatenated here. So for a classification problem, we can use 0-1 coding for a classification problem. For the case of 3 classes, you can have 3 output neurons with the 0-1 coding. So the learning in Rvfl is very simple, as I mentioned before also. Our outputs are computed by dot product between the data and the output weights. Ideally, our output values are expected to match the true labels of the training data. So these outputs O are supposed to match the true labels of the training data. Of course, we may have error here. The output value and the true labels, they may not always perfectly match, and you have the error value here. So this is the output given by the neural network, and this Y is the true label, ground truth. And we compute the difference and square it up as the error value. And the second term is known as the regularization term or minimum norm requirement with the regularization parameter lambda. So this objective function, you can differentiate and equate it to 0. And when you do this, you will obtain these closed form solutions. So we have 2 forms for the closed form solution, and we can select the primal form or dual form depending on this condition. When the number of training samples are much larger than the total features, then we select the first primal form. When the condition is other way around, we select the dual form. By doing this selection, we can reduce the computational complexity. And the computational complexity comes from the matrix inversion here. So we have a matrix inversion. It comes from the matrix inversion. And the lambda is the regularization parameter. The approximation ability of Rvfl has also been proven in the past. So you can look at the original paper from 1995, where they talked about universal approximation property of Rvfl. And recently, this issue was revisited in 2020. And you can also find another proof over here in this archive paper. So as I mentioned previously, a large number of randomized neural networks were developed and published independently. So the consequence of publishing all these works independently is that no one compared them empirically, which one is performing well, which properties are useful, and so on. So for the first time in 2016, we thought about comparing all these randomized neural networks. Even though we say comprehensive evaluation of Rvfl, when we remove direct links or when we remove bias and so on, we will obtain other randomized neural networks. So in our work, we evaluated the importance of direct links, importance of bias, and the scaling of randomization and so on. And a few different activation functions were also considered. Whether regularization is useful, we investigated that also. So this is actually the first work to compare all these randomized neural networks. And these methods were proposed from 1992 to 2004. ELM was proposed in 2004, Rvfl in 92-93 period. So until we did this comparison in 2016, there was no such comparison anyway. And we made use of Friedman ranking, critical difference CD, and so on. So in addition to using Friedman ranking, we can also make use of pairwise comparisons like Wilcoxon test and so on. So we made use of the data sets available from this particular paper, JMLR 2014, and this work is very popular. I think this paper has 2,000-3,000 citations and so on. So we first looked at the importance of direct links, with direct links and without direct links, and with bias, without bias, and so on. So when you see minus and plus, minus sign indicates absence, the plus sign indicates presence. And we are doing all this for the single hidden layer implementation. So in 2015, 2016, there weren't many deep randomized neural networks. So we were looking at only single hidden layer version. And Rvfl without bias and without direct links, it will become extreme learning machine. Rvfl with bias, without direct link will become Schumidt's version, Break's implementation, Guo's implementation, and so on. And Rvfl with bias and with direct links, it is the original Rvfl published in 92-94 period. So we also considered a few different activation functions. We also looked at with regularization, without regularization. In all cases, our conclusion was consistent. Direct links usually lead to better performance overall than without. And the bias didn't have a consistent effect. So the bias had a mixed effect. And we also went on to investigate the regularization. And as you could expect, when we introduce a new parameter lambda, the regularization parameter, and when we tune it, we were able to obtain a better performance. So our conclusion was regularization is useful. Better to have regularization instead of setting it to 0. And the scaling. We investigated the effect of scaling by doing numerical experiments on these data sets. And what we found was the Rvfl is relatively insensitive to scaling. If you look at these rank values here, these numbers are rank values with different scaling values, and with bias, without bias, with direct link, without direct link, different combinations. If you look at the rankings, all the rankings are pretty much 2.5, around 2.5, all of them are. So that indicates the scaling is not very critical here. And what we found was, if the scaling of the randomization is not very appropriate, the neural network will have more hidden neurons. If the scaling of the randomization is good, we will have less number of hidden neurons. So the neural network is able to adjust to a bad scaling by having larger number of hidden neurons and giving us relatively good performance. So that is what we found out. and that is explained here also. The same observation is explained. We also compared the activation functions. As I mentioned to you, the ReLU family is very good for classification. So if you are doing classification, you better think about ReLU family. But among these activation functions, the exponential one was performing better. And the comparison between Rvfl and ELM, the main difference between Rvfl from 94 and the ELM from 2004 is the direct links. Rvfl has the direct links while ELM doesn't have them. So the disadvantage of direct links, when we have direct links, obviously the input dimensions are increasing and the matrix inversion will have a higher dimensionality to manage with direct links. But apart from that, what we found for other factors here, the direct links were very useful. So Rvfl may be possibly using nonlinear features to deal with nonlinear separability, while linear separation can be achieved by direct links. Because of this property, usually Rvfl requires less number of hidden neurons. And the direct links regularize the adverse effects of randomization. This regularization of randomization is required when we go for deep versions. So if you have 5, 10 hidden layers and all hidden layers are completely randomized, at the end of 10th layer, for example, your features are going to be excessively randomized and may not be good. So the direct links can regularize the effect of randomization. So in the context of classification and forecasting, we found out that the Rvfl with direct links are always better. And in particular for time series forecasting, we were able to observe statistically significant performance advantage for Rvfl. So our conclusion is, hence permanently removing the direct links in the Rvfl is not a good idea. And this is what ELM was doing it anyway. So the advantage of direct links is going to be magnified when we go to deep Rvfl. So the evidence of superior performance of Rvfl, there are lots of papers, and all these papers are actually comparing the single hidden layer version. So you have a number of publications and all starting from 2016. From 2016 to now, there are lots of papers comparing Rvfl and ELM, and the conclusion is pretty much consistent. Rvfl with direct links is better, and the first 3 were published by us, 2 in 2016, 1 in 2017. The 2017 version is for visual tracking with randomized convolutional network. So convolutional random vector functional link, and that is for visual tracking. It was published in IEEE Transaction Cybernetics in 2017. So in this paper also we compared Rvfl and ELM, and we found the Rvfl was better, and we had several layers of randomized convolution. So this is more like a deep network as well, because we have multiple layers of randomized convolution. Then this paper is on regression, and this is again time series forecasting, and some others also. For example, this is one of the recent work as well, an unsupervised parameter learning model for Rvfl. Here also they compare with ELM, and they show significant advantage for Rvfl. And this one is a deep structure, multi-layer structure. Here also we compared with ELM, and we were able to show improved performance in this publication also. And I briefly mentioned two recent additions to the randomized neural networks collection. One of them is called Stochastic Configuration Network, published in 2017 in IEEE Transaction Cybernetics. Another one is Broad Learning System, published in IEEE Transaction Neural Nets in 2018. So what are these? SCN and BLS. So SCN is a randomized random weight neural networks published in 1992. So they take this particular implementation and they introduce incremental learning using gradient boosting concepts. So you may have heard about gradient boosting concept. It is coming from about 2001 or 2002. And the researchers proposed this gradient boosting concept, I think, for random forest or decision trees first time in 2000, early 2000. SCN also does not have direct links. And this particular version, Random Weight Neural Networks 1992, I am talking about which one? The first one here. So SCN is actually coming from this first randomized neural networks from 1992. So from 1992 version, they take the 1992 version and then add the gradient boosting concept and then call this stochastic configuration network without direct links. BLS is actually coming from the functional link concept proposed by Pau. They proposed this flat neural networks in 1992 or late 1980s. They call this flat neural network. So in the BLS, the word flat is converted to broad, and then they introduce incremental learning. And also, if you look at the broad learning picture, you will see it has about 2 or 3 hidden layers. But the difference is the hidden layers are placed horizontally. So it looks flat or broad. And all hidden layers are connected to the output layer. So BLS is placing 2 or 3 hidden layers horizontally and connecting them to the output layer. BLS also exclude direct links. So in our opinion, randomized networks that do not have direct links may not perform well if you want to have deeper versions. So in the original 2018 TNLS paper, BLS was found to be worse than hierarchical ELM. So hence we can conclude that deep Rvfl can easily outperform stochastic configuration network and broad learning. So these are the two references, SCN reference and the BLS reference. And we actually recently did some comparison between these methods, and we found that the SCN and BLS, the original versions, were performing really badly. So compared to all other implementations of neural networks, the SCN and BLS are not performing well here. So we compared with a large number of neural networks, and all these neural networks are given here. The full names are given here. I cannot give you more details about this because this is under review now. These implementations, these are improved Rvfl versions. These versions are under review as a second submission, review as R1 submission now. So I may not be able to give the details of this, but these comparisons are going to be useful to you anyway. And these are the methods that are coming from the literature. So we propose deep structures, deep Rvfl, And when you look at the computation and implementation, you will see we are actually making use of the original equations. The original Rvfl closed form solution can be used for the deep structures also. So we presented two configuration. One is deep Rvfl with multiple layers of randomization. Another one is ensemble deep Rvfl, and we found this one is to be very interesting and very useful, and we are able to extend this very easily to many versions, and the improvements are very significant as well. The original version, you can find it as an archive paper. Recently it was accepted by pattern recognition, so the accepted journal paper, I will show you the reference of the journal version as well in the next slides. So we will look at the deep Rvfl and the ensemble deep Rvfl. First, the deep Rvfl, and instead of going through the text here, maybe I will just show you the picture. So this is the deep Rvfl version that we suggested, and this structure is similar to the deep echo state network as well, ESN. So some of you may be familiar with deep ESN, and this structure is very similar to deep ESN as well. I think deep ESN is maybe about a couple of years older than this deep Rvfl. So you have the input layer and multiple hidden layers, up to L number of hidden layers, and all these connection weights are randomized. All these connection weights are randomized here. And we collect the features from hidden layers. Every hidden layer, the outputs are collected and the features are concatenated. So once you concatenate all these features, then you apply the same closed form solution. But the dimensionality is certainly increased here. But the final solution is the same. You can make use of the same final closed form solution, but the notations may be slightly changed to introduce the hidden layer numbers. So you have hidden layers, and the number of hidden layers has to be considered here as well. So for that, we introduce the hidden layer numbering in the superscript. But otherwise, the closed form solution is exactly identical to the basic Rvfl, no difference at all. So this is the deep Rvfl we proposed. Then we have the ensemble deep Rvfl. We made a small change. Instead of concatenating all the hidden layer outputs and computing the connection weights only once, we decided to compute the connection weights for each hidden layer separately. From each hidden layer, we obtain outputs. From each hidden layer, we obtain outputs. So for the classification, if you have L number of hidden layers, you are going to get L outputs, output values. So when you have multiple output values, we can make use of the ensemble methods. The simple one is majority voting. So for example, you can use majority voting from all these outputs and obtain the final output. And we found this version to be really interesting. So for most of our current extensions are based on this ensemble deep Rvfl version. Again, as I mentioned to you, the equations are pretty much the same. The selection between primal solution or dual solution, all these are the rules all are the same. And you can refer to the previous slide, learning in Rvfl. And the same equations are used again, but we are using the same equation multiple times because you have to use the closed form solution for every hidden layer separately. The closed form solution is used separately for every hidden layer. And this paper, this version is published by Pattern Recognition in 2021. And we did extensive comparisons with ELM, Rvfl, HELM, and so on. The comparison results are here. And as you could expect, the ensemble deep Rvfl performs the best. It is better than the deep Rvfl. So the deep Rvfl is worse than ensemble deep Rvfl as we expected. And the extension to deep structures that we proposed is a general concept. So we were able to apply the same concepts to the SP-Rvfl. This is an Rvfl variant published in 2019. So we took this Rvfl variant published in 2019 and we extended it to a deep version. Just to illustrate, the extension to deep Rvfl is general. And we compared the SP-Rvfl original and the deep SP-Rvfl and ensemble deep SP-Rvfl. As you could expect, ensemble deep SP-Rvfl the best one, then the deep SP-Rvfl and the original version. So you can see these results, all these results in our archive paper. So the archive paper has all these results. And the problem with deep neural network, the randomized neural networks, and in particular deep randomized neural networks, is parameter tuning. Even though the randomized networks are really fast, how can we select the number of hidden neurons, number of layers, how to find the regularization parameter value, the 1 over lambda value, how to find this value, how to find the number of hidden layers, how to find number of hidden neurons. All these were really time consuming. So we tried to propose a two-stage hyperparameter tuning, which is a little bit faster than one-stage tuning. So what we did was, in the first stage, we tried to identify approximately the suitable number of hidden neurons, a suitable value for C, and then a good activation function. So we did this coarse to fine search. So in the first stage, we will do a coarse search, and in the second stage, we will do a fine search. So in the first stage, we look at a few different values, only 3 different values for the hidden neurons, depending on number of training samples. When the number of training samples are in this stage, we considered hidden neurons at these values. When the number of training samples are larger than 10,000, we considered this number of hidden neurons. So in the first stage, we will train only 2 hidden layers EDRVFL. So the depth of the EDRVFL is also very small. L is restricted to just 2 layers. The objective is to find which is a good value for number of hidden neurons and which is the good value for C with just 2 layers. So once you find the best value in the first stage for the number of neurons, in the second stage, the best n value is slightly scaled, 0.8 times, 0.9 times the best value. And then we do a fine search for the number of hidden neurons. The first stage tuning for the number of hidden layers, we restrict it to just 2 layers in the first stage. In the second stage, the depth is increased up to 10. So the details you can find in this paper. And for the selection of activation functions, we realized that these 3 were enough. Even though we are listing 8 activation functions, if you use just 3 of them and select among these 3 in the first stage, that would be enough. So the activation function was tuned only in the first stage. So it doesn't go into the second stage. We also found out the batch normalization can be useful. So the deep neural networks have a few different normalization methods. So you can consider using one of these normalization methods also. And nowadays we commonly use this output normalization or batch normalization or whatever, neuron normalization. So there are several variations and you can consider using them also with randomized networks. The tuning of the C is also pretty much the same. We select a C value in a coarse manner in the first stage. And then in the second stage, we do a fine search. The best C value divided by 4, best C value divided by 2, multiplied by 2, multiplied by 4, and so on. So it is a coarse search to fine search strategy. And what we found was the C value is very important to the performance of ED-RVFL. So the tuning of C is very important. So in the pattern recognition paper, we included a large number of deep neural networks. As you could see, self-normalizing neural networks, ReLU activation without normalization, weight normalization, highway networks, layer normalization, batch normalization. So we considered lots of deep neural networks, ResNet, and the basic Rvfl, SP-RVFL, deep RVFL, and all these were considered. And the details are in the pattern recognition paper. We used about 45 UCI data sets. And the results are given here. So the ensemble deep RVFL performs the best, and you can find the details in the pattern recognition journal paper. In the first version, there is no statistical difference between the randomized neural network and the SNN, self-normalizing neural network. There was no statistical difference. But in recent times, we have developed several improved versions for ED-RVFL, and all these improved ED-RVFLs have a clear statistical advantage over SNN and all others. For example, the result table I showed you here, this is a very recent work. And so this is our improved ED-RVFL, and these improved ED-RVFLs are statistically better than all these deep neural networks. So the star sign is placed here to show the best one is statistically significantly better than all these. So this is our most recent work, and I am not explaining much about this because it's still under review. So in summary, we introduced randomized neural networks starting from 92, and we evaluated the older methods with a single hidden layer. Then we went on to propose deep RVFL, ensemble deep RVFL. We also have another version based on autoencoders, stacked autoencoder based deep RVFL. This one was published in applied soft computing in 2019. But remember, auto-encoder training is iterative. So whenever we have auto-encoder training, it is going to be iterative one, not the closed form one here. And EDRVFL, the performance is very competitive. It can now beat these deep neural networks also. So very competitive performance nowadays with fast training as well. So what are the limitations? The limitations of these randomized neural networks is that in most of these, we didn't include CNN. So that means if you want to apply these methods on image data sets or video data sets, then you need to apply CNN to extract features. So if you apply CNN to extract features and then apply Rvfl or ensemble deep Rvfl, the performance will be very good. And we have done some work like this, and such papers are under review as well. So in this presentation, we mostly consider tabular data with ensemble deep Rvfl. So once you apply CNN and extract the features are going to become tabular as well. So then you can use ensemble deep Rvfl. So with this, I conclude my presentation, and then I will look at the questions. There are some questions or some comments or whatever. So I look at the first one. Are they only single feed forward hidden layers in Rvfl? So we, in our deep version, we have connections between different layers. So this one can be generalized, and we have already done that as well. Again, the paper is under review. I didn't include that. So we have connections between all the layers. That is also possible. We have done that. And if you look at the ensemble deep structure, this particular structure has some connections like this, but this is limited. We have also introduced connections from arbitrary hidden layer to another arbitrary hidden layer. So we can also introduce such connections. So this is not a problem anyway.
Can you hear me?
Yeah, I can hear you. Yes.
Yeah, I can hear you. Yes. Okay, thanks. I haven't been very successful with the microphone in the conference, but you did explain that. That question about the multiple layers was my presentation. So that became obvious. And also, I had a second question on extreme learning machines, and you also went into a great deal of detail and explained that. So those questions I posed earlier were addressed. First of all, thank you very much for the overview. This has really helped me put things in context, and also it's pretty exciting. Somebody results that, especially the one that hasn't been published yet. Just the other question I had to transfer learning and explainability. And I wonder if there's a huge advantage in that you're not using these, sledgehammer, heavy duty universal function approximator, deep learning neural networks, CNNs and the others. You actually have an opportunity to get much cleaner, more expressive networks with RV would be my guess. So have you been looking at transfer learning and explainability?
Transfer learning, we haven't tried much.
Transfer learning, we haven't tried much.
I think there's a loop, I think. Is that right? Maybe you need to close the microphone.
Oh, sorry.
Yes, I hear my voice back. Okay. I think transfer learning for a closed form randomized method may not be very advantageous because it's completely randomized, and you have closed form solutions for the output layers. So in this case, the transfer learning may not be very much advantageous, but online learning can be useful. So the online learning means you are receiving the data sequentially, like time series. So then you need to update the model, and that can be done. We have online Rvfl models for time series data, but the transfer learning is not very beneficial here because you have closed form solutions. So in that case, you can actually do a training in one go. And if you are going to do differently, then it is going to be online. So you have your previous data and you use the previous data to train your Rvfl, and you have new data. Then you can do the online version. So that will be more like the transfer learning as far as I could see. And explainability, yes, I have some ideas, but I don't have the PhD students or research students to test it. And I have a strong feeling that explainability with this ensemble deep Rvfl will be uh, very much easier. And we may be able to come up with the rules particularly for the given test data. So when you give a test data for that particular sample, we can come up with special rules why we are coming up with this decision. So the test data based rule extraction will be possible. That is what I think. But then I need to have researchers to explain that, to do the work as well. Any other comments?
That sounds really exciting.
Yeah, thanks. Thank you so much. So you have anyone with any other comments or questions?
Can I have a question?
Yes, please. Yeah.
Thank you for your very interesting and inspiring presentation. I have a question about random parameters. Could you explain how do you select random parameters in this deep architecture? Because my experience are that these two parameters, I mean weights and biases, should be separate, should be selected separately because they have different functions. So could you explain how do you select these parameters? Thank you.
So as I mentioned, I think previously, what we found was that uniform randomization between -1 to +1. That is what my students are using in all our codes. That's what my students are telling me, and they said that was fine. But recently what they found out was with this randomization, we can include some normalization methods commonly used in the deep neural networks. So when we use these normalization methods that are commonly used in deep neural networks, I think to some extent we are rectifying the problem with this fixed randomization. So if the fixed randomization is not particularly good, then the normalization procedures are going to fix it. That is what's happening now for us. And most of the time, our input features are normalized as well. 0 mean variance 1. And we can do this for the hidden layers also. If you want, you can also renormalize the hidden layer features coming out of the hidden layer neurons. You can do the renormalization there also. So according to my students, there is no need to adjust this one. That is what they have told me. And we have tried regression, time series, and classification, tabular data classification. And for all these things, these were fine. That is what we found out.
Okay, thank you very much for your answer. In my shallow randomized neural networks, this interval is very important. And as I said, I separately generate weights for from some interval, and then I adjust biases. Thank you very much.
Yeah, but I think you may be correct. For single hidden layer version, you may have a problem, I think. But when you go to the deeper structures, they become even more insensitive to these ranges and so on. Yeah.
Okay, thank you.
So the other distributions with non-Gaussian, I didn't listen to the plenary talk, so I think it may be possible. There are other normalization. I think my students are using some linear transformations and so on. I think my students now try 3 or 4 different normalization. In addition to this zero mean variance one, they have 3 or 4 different normalization nowadays, and they are using different normalization in different papers nowadays. So we are also exploring it. Yeah, that's right. There are different normalization functions like linear transformation, and this like y is equal to ax plus b and that kind of things. So you have these a and b parameters to tune. So my students have tried all these, and yeah, we are looking at a few different normalizations. Yeah, that's right. So then with this, I can pass to Massimo 2 minutes ahead of time. Yeah. If you don't have any other questions, yeah. Is that okay? Yeah, Massimo,
Okay.
please. Yeah, please. I had to stop sharing, I think.
Yeah.
Yeah, I think I stopped. Yeah.
Can you hear me see the screen?
Yeah, I can see you.
Okay. Thank you very much, Professor Suganthan, also for your very exciting part of this tutorial. Just a few words to present me. Massimo Panella. I am from the Department of Information Engineering, Electronics and Telecommunication of the University of Rome La Sapienza in Italy. I'm working on neural networks, machine learning, and computational intelligence applications since about 1995. So now I'm a full professor of machine learning and circuit theory and electrical engineering at my department. So my idea in this my idea in this part of the tutorial is to focus on the application part of time series forecasting. We will see at the end some insights about the theoretical findings on distributed learning, federated learning, or randomized architectures. But anyway, I would like to focus on practical aspects that are very popular when you try to apply both shallow and deep, in particular deep neural networks for time series forecasting. And I will focus on some real-world engineering applications rather than, for example, natural language processing and so on, that are most relevant for computer science applications. and in particular in the energy optimization domain, for example, to predict the production of energy power in photovoltaic power plants, for example. In general, when you try to solve a time series forecasting problem, you are dealing actually with a regression problem, because this is an example, a very popular example based on a linear predictor, where if you have a time series S, we will refer obviously to an integer time index n with a normalized time samples. And we have a time series S of n, time sample n. The problem is to forecast future values, one or more future values of the time series, based on the knowledge of past samples of the time series. So in general, and with the linear predictor, what you are doing is to estimate the new sample at the distance m. In general, m is equal to 1, but as we will see, especially in electrical engineering application, you have to forecast, for example, a whole day ahead in order to optimize your energy sources. So this value, especially in actual applications, might be greater than 1. And this value is linear combined in a linear predictor with past values of the time series. Okay, then you can have, of course, a recursive approach, where another regressive approach where new values are estimated based on the estimated samples. But okay, this is a very old theory, and this is not the focus of this tutorial. So also how the parameter are estimated. But what you are doing implicitly in this case is to embed what is called an embedding technique, is to embed past samples in a vector that is used to estimate the output. So this is a function in an n-dimensional domain with an output domain which is a scalar value and estimated. There is a lot of theory, especially when the time series is noisy, is chaotic, for example, in biomedical applications. And in these cases, there are some approach that can be adopted in order to select wisely the number of past sample to be used. This is a typical question that always is present, even now in any presentation, even the presentation of our paper last Sunday, in the first day of the conference. A typical question is, how many past sample did you use for estimating the new one? Or how long is the training set? Okay. So there are some approach that can be used for estimate, both theoretical or heuristic, to select the number of past samples and which past sample can be used. Okay, not necessarily, sorry, consecutive past samples. Okay. Anyway, the other obvious step is that the function, in order to deal with real world application, the function that applies to this vector of amended sample should be a nonlinear function, usually a complex nonlinear function, which is estimated in a data-driven way, because we have the observed time series, so we have the past samples. So it is a pure data-driven approach, and this is completely meet the paradigm of neural networks. Okay. So in general, just a few words regarding the embedding theory, where we have in general nonlinear oscillator or nonlinear system which produce the observed time series based on an internal state and two nonlinear function in general. This is represented in a discrete time, okay, domain. So embedding theory aims at reconstructing or estimating the internal state of the system, and the neural network can be used to approximate the nonlinear function linking the internal state to the output observed sample, or the new state, in order to estimate to forecast the new sample. So in this case, we have a prediction based on this nonlinear function, the estimated state based on embedding, and a data set based on a number of pairs of input and output, okay? In general, coming from some results of physics, this embedding is obtained by using D samples, but not consecutive samples, but with a time lag, in general called T. This time lag is usually estimated by using, as we will see, Shannon average mutual information, because samples should be sufficiently distant in order to bring out some new information, but not so distant in such a way that they are independent. And this value is the embedding dimension is associated with the internal state dimension, so it's also associated with how to say the problem dimension. Okay. We also presented in the past a phase-space approach, where instead of predicting directly the new sample, we focus on the prediction of the new state in such a way that the prediction is regularized, because we will predict all the future samples in the new state, in the new embedded state, and then we can pick up the interest value within the forecasted state. Okay, and we will demonstrate it about 15 years ago that this by following this approach, we can obtain a kind of regularization. Okay. So as I said, the typical routines are the average mutual information for estimating time lag, the embedding dimension to estimate the Fresnel-Niebuhr algorithm to estimate the embedding dimension. Then we can estimate also the level of noise or the causicity of the time series if necessary. But there are also some advanced methods produced in the literature or the years, based on genetic algorithms, for example, other heuristic approach, and as we will see, especially in this tutorial, by using deep neural networks, because we will see deep neural networks have the property to, in the first layers, to produce a useful new representation of raw data, the input of the network stack. And so by using deep neural networks, we can obtain an automatic and implicit embedding in such a way that the internal state is represented efficiently based on the adopted architecture and the subsequent layers. Okay, this is typical of deep learning. For example, this is a way how heuristic embedding based on genetic algorithms can be adopted, where a chromosome representing an individual, so a possible solution for embedding is a binary string, where 1 means that the best sample returned in first position means n-1, so the precedent samples, and 0, these samples is not used. So this is an example. There are two possible codes that can be adopted for genetic embedding in order to have to produce an embedding in a heuristic way. And this is typical used. This was used before deep learning with shallow neural networks. Okay, I will come back because what has been discussed by Professor Suganthan was very interesting regarding the properties of randomized shallow architectures like Rvfl, but even streaming machines and so on. And okay, in these cases, an embedding is usually necessary unless you are using recurrent, as we will see in a few seconds, recurrent neural networks, where you are using a recurrent part in order to implement a dynamical system. In sequence or time series, I will use sequence, which is a mostly a European term, or time series equivalently. Okay, in sequence or time series processing, we have two main problems. Next sample for prediction, next step prediction, and so if you went through code in Python or MATLAB, in TensorFlow, Keras, MATLAB, you know that when you're using an LSTM layer, for example, you have to specify if the output is the last state or the entire sequence. Okay, when you deal with next step prediction, the input is a time series and the output is a time series. Okay. And for each input, you would like to, you want to predict, to forecast the future one. Okay, but of course there is another important field of application of deep recurrent neural network for time series analysis, not forecasting, which is time series classification, where you have at input the whole time series, and the output is a label classifying that time series. Okay, in this case, you can also use bidirectional architectures, because you can violate the causal property of time series based on the time domain, because you have the whole time series during the training phase. I will focus here in this first, given the limited time, I will focus in this this kind of problem of next step prediction, time series forecasting, and so we have to deal with causality. It is a problem, okay, because we don't have the time series observed at the end. Okay, when we are predicting a sample. First approach were based on time delayed network. This is pretty equivalent to an embedding, because we have embedding at input. This is a consecutive embedding, just like in the case of a linear predictor. But for example, in this case, a multi-layer perceptron, an RBF or adaptive neural fuzzy inference and NFS fuzzy inference system can be adopted as a nonlinear function that can estimate the future value of the time series yn based on the delayed input. Okay, this is equivalent to embedding. A very popular innovation was based on Hellman network, on a simple recurrent network, where some internal output of the system are fed back to the input. So in this case, this was the first proposal of a recurrent approach where the neural model was able to how to say, to implement a true dynamical system, okay, with an internal state. What's the problem? You may know the problem is training, okay? Because in this case, we cannot, although we can demonstrate that universal approximation is assured and theoretically is very powerful, but with our network, the real problem was the training, because gradient-based backpropagation algorithm cannot be applied directly. And so, as you may know, we have two directions to solve this problem. One direction is randomization. The second one is backpropagation through time that has been developed especially for deep neural networks. There are a lot of recurrent shallow architecture like Hellman or linear autoregression with exogenous inputs and so on. But they were all characterized by high computational training cost and slow convergence. Possible convergence to poor local minimum, because function is strongly non-convex in this case. And also vanishing gradient problem, even in the case of this mostly applied to deep stack, of course, rather than to shallow stack. But the problem instead is in learning long-term dependencies, and this has been solved only by the introduction of LSTM layers and GRU layers, for example. Just a word regarding the fact that usually recurrent neural network for time series forecasting are based on Markovian behavior of time series, which means that the output depends only on the previous state. Okay, and this is the implicit assumption that always hold, especially for shallow recurrent neural network, as for example for ecostate networks. So we'll see. Reservoir computing, in particular ecostate networks, as I said, but Levy state machine, backpropagation, decorrelation, Evolino, and many other ones are based on this assumption. So we have a dynamical recurrent nonlinear part, which is the reservoir, okay, which implemented the dynamical recurrent part. And in this case, in reservoir computing, this recurrent part is randomized in such a way that training is not necessary. And only the readout part, which is typically linear, so we have a model linear in the parameters, as we will see. This readout part is trained, and usually by a regularized least square approach. And the efficiency is really relevant to the Markovian training that is restricted to the linear readout only, which depend on the current state estimation. And characterization of the contractive dynamics, the ecostate property, in order to have contractivity, stability of the whole system, is in the reservoir part. So based on what we discussed so far, the reservoir estimated by XN at the output of the untrained randomized, because these two matrices, W in and W hat, are randomly selected. And this is a typical dynamic equation of a dynamical system. This state is a representation of the time series, and the input can be both a vector, so an explicit embedding that can be applied, or it can be either as even a scalar input, so the scalar time series. And in this case, the state is will be an equivalent representation of an embedded state. Okay, and then there will be only a linear combination of the two to obtain the output. But of course, even nonlinear function can be applied at the output, but the training difficulty is, if the nonlinear function is invertible, there is no problem, because we can train the readout by a linearly square approach. Extending to deep learning, recurrent layers are stacked in deeper prediction models, where we can have more than one recurrent layer. As we will see, LSTM is a typical recurrent layer in deep learning. And they are able to deal with long-term dependencies, which is very important because, in ecostate network, you have to reach a trade-off between memory and stability and internal state dimension, so problem dimension. Instead, in LSTM, they are more deep neural networks are recurrent. Deep recurrent neural networks are more flexible in this sense. Although they may suffer for the vanishing gradient problem, okay, because we have more stack, and it is typical of deep architectures. What is not really, especially for students, the first approach to deep recurrent architectures is that usually the architecture is represented in an unrolled, unfolded fashion, which directly applies to backpropagation to time, which is the algorithm that is used for to estimate parameters of a recurrent layer in a deep neural networks. But actually, the architecture is a rolled dynamical architecture, like so far, of course, with a retard in such a way that the algorithm is computable. The layer that can be used are most popular ones are long short-term memory layers and get recurrent units layers. They are slightly different. In GRU, there is a more compact representation, a more, as I say, hysteretic switching between long-term dependencies, very old information and new information. And they are compared with a typical shallow layer in reservoir computing, okay? So how embedding is obtained can be obtained in deep neural networks. For example, this is a typical, very, how to say, reference architecture, where we have the input of the time series, a scalar time series, an LSTM layer, and then a fully connected layer, both with linear or nonlinear activation. Usually, ReLU activation, nonlinear activation is better to be adopted in deep stacks. Okay, the embedding, so the internal state representation is obtained implicitly at the output as the output of the hidden state of the LSTM layer, okay? It's HT, okay, which is the output. While the cell state is only used internally in LSTM for managing the four kind of cells within each LSTM layer. If you are using, for example, two LSTM layers, for example, in an encoding, decoding, so an auto-encoding system, you can obtain the embedding at the output of the first layer, and then after the output of the second layer, there would be an encoded state. Okay, it's a problem of architecture cross-validation. If the number of hidden sets of the LSTM layer in the second layer is larger or smaller with respect to the first one, this is a typical problem of deep learning, that we cannot optimize all the architecture and algorithm hyperparameters. So it's also a matter of experience in this case. But in general, you can imagine that you have the embedded state at the output of the first layer and encoded state at the output of the second layer. But of course, using LSTM layer, you can also put at the input a vector instead of the scalar time series. So an explicit embedding can also be adopted at the input of the LSTM layer. And then at the output of this layer, we will have an encoded state, okay? And of course, the larger the number of recurrent layer, the larger the transformation of the encoded states, of the encoding of the states. Likely reducing progressively the number of hidden cells, so the dimension of the internal state representation. The next step towards randomization in this case is based on the use of convolutional layers in addition to recurrent layers. Convolutional layers are feed-forward layers, okay, not recurrent layers, but they can be used to filter the time series. In general, filtering of time series means that we can abstract some useful feature representing the time series, okay, in a univariate approach. I will distinguish between univariate approach, where a single time series is adopted to forecast new samples of the same time series. But in an increasing number of actual problems, we have to deal with multivariate approach, where more than one time series is present at the input of the system in order to forecast a new sample of one of the time series, for example, S1. Okay, and as we will see, this is typical where when we use, for example, weather data like wind, temperature, wind speed, wind direction, irradiation, sun radiation, in order to forecast the output of a photovoltaic plant, which strongly depend on the climatic condition. Okay, so in this case, the frame of the convolutional layer can be used in different ways. We propose a different approach in this case. For example, the simplest one is considers that each row of the convolutional frame of the input to the convolutional layer is a time series, okay? And each column is a sample of this time series. The time series usually are timely aligned, and an embedding is possible here in each line, okay? And so the filtering of this convolutional layer, and then you can use, of course, more than one convolutional layer, can be used in order to extract the feature representing the aggregated relation or correlation among the input time series. Okay, this is the main idea. Then, after a number of, okay, you can use batch normalization, you can use dropout, you can use pooling, okay? The filtered and aggregated, so this is a kind of aggregation that we obtain, can be passed to the recurrent layer. Another approach can be based on algebraic aggregation, based, for example, upon data among between two time series and so on, okay, with a similar stack. This also was proposed. I have to speed my presentation because I only about 20 minutes. This is an example of some results about multivariate analysis, where we have demonstrated that if we want to forecast the output power of photovoltaic plant in a day, by using only in a univariate approach, only power at the input to forecast power. This is the result by using a typical stack based on LSTM. But when we use compounded approach based, for example, on power and temperature, power and wind, or power, temperature, and wind, prediction accuracy can be improved. Okay, this is very very typical. Of course, not always this happens because the insertion of further time series should bring new correlated information and not uncorrelated, independent, or noise-like information that can impair the prediction quality. Actual open issues are the architecture validation. That is typical of deep learning because we have a lot of hyperparameters, and not all of the hyperparameters can be cross-validated assessed. And the problem is also that in time series forecasting, when we have to deal with causality and not with for example, in time series classification, where we can use bidirectional layers, we have all the time series. The problem is that cross-validation is very critical, especially for non-stationary data, because if I have a training set of a number of days, for example, like this one, photovoltaic power strongly depends, for example, on clouds and rain. Okay, if I try to cross-validate on the day before, and the day before was raining, cross-validation, the behavior of this training set will be very different from one of the set. So there is no some of the typical assumptions that we use when we deal with theoretical learning are not satisfied. Okay, so it's very typical, especially because data are not stationary. So there's a problem with data fusion integration. We are dealing with convolutional layer, but where we can have some very different kind of information. For example, we would like to integrate numerical time series coming from the observation of physical parameters like temperature, wind, humidity. But we can have other kind of information represented by, I don't know, by some sentences, like, for example, weather forecasting, the presence of clouds, and so on. And another problem is model explainability. So at the first glance, randomization can help us to speed up the training optimization process. And so we can try to cross-validate more hyperparameters. For example, in order to estimate the right number of LSTM layers, the right number of hidden cells for each layer. And also to regularize data, because randomization equivalently insert an inherent noise, in data, so this can bring a kind of regularization. Okay. Key point of regularization is that there are suited trade-offs pertaining to accuracy, complexity, usability that always exist between fully trained and randomized architecture. Theoretical findings about approximation capability are soundly proven in the literature. Convolutional neural networks, convolutional layers with randomly generated feeders may achieve only a small drop in accuracy in addition to the reduced computational cost for training. But actually, this has been proved for image filtering and video analysis, image classification. But for time series forecasting, where these layers are used together with recurrent layer, there is still is yet to be well assessed. Okay, the improvement or the reduced drop of accuracy made by randomized layers. We presented this year at IJCNN an approach based on a randomized predictor. In this case, we have a convolutional layer randomized, a flattened layer, and an LSTM layer fully connected. So it's a very standard architecture, but instead of using a trained, we studied we compared the performance when the convolutional layer is trained or not in a multivariate approach. And in this case, the frame is based on a circular embedding of the time series in such a way that by filtering, we should obtain a combination of all information based on the dependencies at the input. And what we obtained, and as we proved, is that the randomized, the multi-day head approach has performance which is better with respect to standard LSTM, okay, so by using convolutional layer, but with respect to the trained, we can have also better performances, and this is due to the fact that randomization inherently regularizes data. So we don't have the drop, but even we can have an improvement of the performances. And this kind of approach, these results are currently under further development. We are submitting a full paper in this regard. Just to conclude, let me resume my soul of electronic engineer, and just to find some interesting connection with the first part of the tutorial. Okay, deep learning architectures are very interesting for some reasons that we discussed, but there is an increasing field of an increasing interest in the development of machine learning models into smart sensors, which are very cheap, which are sensor based on a communication system and a computational system with usually some constraints regarding the computational capability and the energy and low energy consumptions and so on. So in this case, it is impossible to implement a deep neural network on a smart sensor. Rather, we can implement an Rvfl, for example, an ecostat network, so a randomized shallow network, okay? The main idea is to put intelligence on board for classification, prediction, interpolation, decision-making, filtering, in biomedical application, in automotive application. Bosch, for example, in Europe is working hard. ST Microelectronics is working hard in this. We have some collaboration with my department, with these companies for the implementation of machine learning models and algorithms on smart sensors. The key word is edge computing. Okay, so pushing artificial intelligence to the edge, because always communication based on low latency protocols of 5G, 6G, 7G will allow us to have a real-time distributed system that can be implemented. And fast randomized, either shallow or deep, but rather shallow neural network models become mandatory for implementation. Okay. In this case, we developed during the last years some distributed randomized models. Distributed randomized models are models where there is not a centralized authority that collect all data and produce a result, but data are left locally to the sensors, to the node, and nodes can exchange among their neighbors only a few model parameters, not data. And this is very interesting with respect to privacy preserving issues, which is a very sensitive problem. And this kind of approach were called during the year distributed, diffused, and now the most popular term is federated. Although in federated learning, there might be some centralized systems that can handle data, but in our case, the approach is purely diffused, decentralized, with no centralized authority. Okay, so we developed the model for ecostat networks, and randomization is very important because by using randomization, we can have model essentially not trained locally because the reservoir part is left locally on the model and it is randomized, so we don't have training. We have to train the readout, so the model is linear in the parameter, even if we would have we had a nonlinear activation function, but if invertible is not a problem, so we have to deal with a linear estimation problem. And this linear estimation problem can be distributed, diffused. So this is typical, which means that we have to, instead of find a regularized solution, typical regularized solution for a centralized model, we can obtain, we can follow two approach by using a distributed average consensus, where the model parameters represented by theta serialized in a column vector theta are exchanged among the neighbors. C is a matrix representing the connectivity, the topology of the connections of the neighbors, which means that if the element C, E, J is different from 0, there is a link between two nodes and 0 otherwise. So there is a very popular DAC protocol that is able to achieve convergence to the average of the whole parameters of the whole node, the parameters of the whole node. So all parameters will estimate the same readout, okay? Leaving the reservoir part, the dynamical part locally, okay? And we also developed an extension of the DAC protocol by using the alternating direction method of multiplier, ADMM approach, where we try to minimize the L is the number of nodes. We try to minimize in a regularized fashion the estimation, the linear estimation of the readout part of the whole of the all agents in the network. And we obtained a solution in a closed form by which, by using also that step, we can obtain the estimation of the readout parameters for the network. These are some numerical results proving that by using distributed approach, we can obtain. Okay, in this case, just let me say that this distributed learning should not be confused with parallelization of the algorithm, because in this case we have an overhead associated with the transfer, the communication of the parameters in the neighborhood of each agent. So the main aim of this approach is not to scale up the computation, parallelize the computation. It's the contrary. We have data, so instead of distributing data in order to scale up the computation, we have data locally in each node, and we would like to leave data locally in each node and without centralizing them. So, of course, a centralized approach should be a baseline and by using distributed approach, performance could be similar, but not necessarily better than a centralized approach. Okay, but they should be better than local approach, where data left locally and models agents do not communicate among each other. And in effect, we proved that distributed approach has a performance that is close to the centralized one, where all data are collected into a centralized computing system. But this approach usually sometimes is not feasible, is not possible for privacy issues, for communication issues, and so on. But the performance is better than the local approach. Okay. The same step were also developed for LSTM-based deep recurrent neural networks. Of course, in this case, in a deep stack, there are a lot of, the problem is more challenging, okay? By using the distributed, average consensus protocol, it is possible to reach consensus on all the stack parameters of all layers of a deep neural networks, okay? For the LSTM layer, but also for the final dense layer, also for the previous, for example, other LSTM layers or convolutional layers. And we proved that also in this case, the distributed system is even better than the centralized one, okay? But we proposed last year at IJCNN also an ADMM-based LSTM approach, where if we adopt randomization in the first layer of the deep stack, the model and we leave free for training only the final dense layer, so the model become linear in the parameters once again, and the parameters once again, and so has the model linear in the parameters if we randomize or if we use an alternating training, okay? But we have fixed all the parameters in the first layer, and we have to train only the parameters of the final dense layer. We can use an ADMM-based approach also for LSTM-based deep recurrent neural networks. Of course, the algorithm is more complex. We have published it here. But we demonstrated that also in this case, we proved that distributed approach is better than the centralized and the local one, okay? By using the same problem. Here is represented, this is a typical database of photovoltaic power plant at Oak Ridge in Tennessee, USA, made of 4 nodes with us. This is typical graph for 75% of connectivity. Okay. Just to conclude, these are other references in addition to the ones based on our publications. Let me spend a few words regarding our task force on randomization-based neural networks and learning system, which is an IEEE task force. I am currently chairing this task force together with Professor Suganthan and Claudio Gallicchio from the University of Pisa, always in Italy. And these are the other members. You may take a look at our website, and if you feel appropriate your interest, you can ask us to join the task force, okay, and to share your activities in our task force. This is the link, is a very simple link to our website, when you can also find the recent activities of the task force. Okay, so I have concluded my talk, and if you have some questions, so I'm here. I couldn't see the chat, so let me say me see if there is something in the chat. Do you have any comments on determining causal relation from time series, time length, grandeur, etc.? I discussed this this topic. I didn't mention grandeur causality, but regarding time lags, etc., usually there are three possible approaches, as I said. One is to adopt some useful heuristic algorithms based on nonlinear system identification. For example, for time lag, the average mutual information, which means to find the first minimum, the optimal time lag is associated with the first minimum of the Shannon average mutual information in order to have an adequate sweet trade-off between independence of data and correlated information brought by data. And another possible way is to adopt a meta-heuristic approach like genetic algorithms, for example, as shown. And the other one is to use recurrent architecture, both shallow or deep architecture, where embedding is obtained implicitly in the output of the reservoir or of the recurrent layers. And when we obtained an embedded state, an internal state representation of the system generating the observed time series, so we also have an equivalent representation of time length causality among past samples. Okay. Second question is, many complex systems have very different predictors across time scales. Do you have comments on multi-scale analysis of time series and not your spatial temporal? Okay. This is a very interesting question. Of course, I didn't have the time to discuss about all these topics in 1 hour. Of course, spatial-temporal data is a very interesting topic regarding, for example, optimization in logistics, in biomedical networking, or in general networking systems, okay, in biomedical, in biologic networks, and so on. And in this case, of course, the use of convolutional layers is very important, because this can be used in addition to attentioning for in order to deal with data coming from two essential domains, which is time and spatial domain. Regarding different time scales, before deep learning, the main approach in this case was to use filter banks, for example, in order to transform data in different time frequency subdomains, for example, using wavelets or other kind of filter bank analysis, and in order to obtain estimation prediction in each subfield, in each subset of the time frequency domain, and then aggregate them at the output. Okay, we had some publications about this in 2004, 2005, up to 2005. Using deep learning, if you use a poor deep learning approach, this aggregation, these different time scales can be obtained by using, for example, different channels in a cyclic graph based neural network, not necessarily a serial stack, but in a direct acyclic graph by using different channels and different LSTM layers, we can process the data at different time scale. For example, using different subsampling of the time series and obtain different internal representation that can be aggregated. I hope that this can answer to your questions. Is there any other one? Fractional order calculus is very interesting. I am an electrical engineer working when I was a child on circuit theory and synthesis of electrical networks. And we've seen neural networks as an evolution of classical circuits. And by using ladder scales, ladder architectures of inductor and capacitors, we can obtain fractional systems in which, if we represent the system in the Laplace domain, we can have exponents, non-integer exponents. It's very interesting because it has been proved that, for example, some time series that appear to be nonlinear, the typical one is the, I don't know what is the right term in English, ECZ, the time series related to the heart rate, okay? It was considered for a long time as a nonlinear time series. So a time series observed by a nonlinear system producing this time series. Instead, it was proved that the behavior of the art is a behavior of a linear system, but non-integer, okay? And this is related also to the embedding theory, because in embedding theory, the algorithms were applied in general to fractal systems, where the dimension of the largest Lyapunov exponent is not, or the dimension of the system is not integer. So to answer to the question, I didn't work on neural networks applied to fractional order calculus, okay? But I know that I agree with you that it's still an open issue, because early in 2000, we had some works related in particular to circuit theory, to system model identification, but in neural networks and also in the field of signal processing, we did have further works in this field.
Can I speak?
Please.
Okay. Yeah, thank you very much for those comments. It's been kind of hard finding people that actually have experience. One of the questions I've had for quite some time relates to something like memristors, for which that was the first system that I read through a bunch of papers on fractional order calculus. So if I take the example of a memristor circuit and stability, robustness issues being analyzed with fractional order calculus, there comes out a question. I assume that forever electronic circuits have been designed effectively implementing memristors, but perhaps with multiple components, not just a single circuit, basic circuit, electrical circuit element, the memristor. So is there any big change in memristors? Does it do something in facilitating the train of thought that gives real benefit at the end of the day? Or do you just simply end back with your circuit design at the same tools, framework of thinking that you had before? And then how might fractional order calculus pile on top of that? In other words, maybe there's nothing really new in the electronic circuits because they've been designed to work for a long time and do the equivalent of a memristor. And perhaps the fractional order calculus part, the practical implementations may actually go further than the normal conceptual theoretical approach. What is your feeling? Do memristors perhaps change your thinking?
Thanks for this interesting question. Can you switch off your mic because there is a loop? As you may know, memristor must be a nonlinear system because otherwise it will be equivalent to an electrical resistor. Okay. So we have two directions of development. From a technological point of view, which is not my field, honestly, nanotechnologies, especially graphene-based implementations, are improving the possibility to obtain cheap and effective implementation of a memristor. Really, okay, as a real device. From a modeling point of view, instead, to my knowledge, memristor are, for example, widely adopted to model the state of change behavior of electrical batteries, for example, because they have memory effects based on the chemical processes that can be well modeled by the memristors, this theoretic behavior of a memristor. And I saw that there are some modeling approach based on memristor also applied to other fields. Honestly, I didn't go through these lectures. What I know precisely is that memristors are as models rather than to obtain a fractional order system, especially mostly to obtain, as I said, an accurate memory behavior of the electrical batteries. So in this field, they are adopted. And also that with nanotechnologies, the technological divide regarding the implementation of memristors is shrinking.
Can I ask a crazy question just for fun?
Yep.
One thing that surprised me was that fractional order calculus goes back to Leibniz at the very latest and raised the issue to me of the sort of like war between Leibniz and Newton over who invented calculus. Is it possible that in Italy there's sort of a perception of the invention of calculus and who to attribute to that is impartial and unbiased? And do you have any opinion about that?
I don't know. I don't know. I don't know to answer to this question. We have in Italy a lot of top-level research center and university that can develop that. We have an history regarding circuit theory and circuit models and mathematics. So it's a very interdisciplinary field. So we have to develop more models and they apply them. But sorry, but I don't want to move the focus of this tutorial too much on fractional order calculus with respect to the main topic, which is randomization based on neural networks. Is there any other question? Because we are out of time. Okay, so if there is no other question, let me thank once more Professor Suganthan. I don't know if he wants to say something to close this tutorial. And thank you all for having attended this session.